Thanks very much, Ken, and thank you all for coming. So I don't expect that anybody knows what spin glasses are, and I'm not sure that you exactly will at the end of the talk. But maybe we'll have some fun. So, okay. That's the cover of the book by my collaborator Dan Stein and myself, which apparently there'll be some copies for sale at the end of the talk. I don't know how much I get for each copy. I don't think too much, but also it's a book which it's supposed to be semi-popular type book, and this is the actual cover of the book. The one on the right is the cover we actually wanted. The one on the right is a sculpture by Dale Chihuly, but Princeton Press couldn't get permission from Chihuly to use his sculpture on the book, and so the one on the left, which isn't bad, is sort of the best we could find. You may have seen some images of, by the way, neither of these has very much to do with actual spin glasses. Actual spin glasses are kind of boring looking lumps of metal, which wouldn't make a very good book cover. So we thought, well, let's get something that's made out of glass and kind of looks like it's spinning. The spin in spin glasses have to do with individual atoms or molecules which have microscopic magnetic properties that come from electron spin, which is a quantum version of actual spinning objects. You may have noticed that in the things that we're showing before the introduction started, some interesting looking, other glassy looking, spinning looking things. Those were done by one of my colleagues in mathematics here, Richard Pellet, and the young artist Luc Bernard, computer generated. Unfortunately, I never had seen those pictures. I should have seen them somewhat earlier, but I saw them yesterday when Tatiana, who's the organizer of, one of the organizers of this meeting, said, how about using these pictures? And I sent some copies of those to my co-author, Dan Stein. We both agreed if we had seen those a year ago when we were choosing the cover art, that probably would have been what we would have chosen. It's really very nice. Maybe in the next edition. So here are some other collaborators in Dan and my work on spin glasses. We're not going to, in this talk, going to get into hardly any technical details, but in the book itself, there are a few sections which get a little bit more technical, and those are some of our collaborators in that work. So the story that is both told in the book and what I'm going to try to tell in this presentation is how spin glasses, how ideas that were generated by spin glasses, which we'll say something about what they are beginning to be used in completely unrelated areas of science and technology and biology, which have to do with various kinds of complex systems, and some of the ideas that originated with spin glasses seem to be useful in these other areas. So we'll talk about what is a spin glass, this boring looking piece of metallic alloy. Why are they potentially of interest in various other areas of complex type systems? Originally in physics and mathematics, we'll talk a little bit about condensed matter physics and statistical mechanics. What kinds of issues come up in various kinds of complex systems? And here are some examples of complex systems. Neural and genomic networks. We'll talk about something called the traveling salesman problem, which is an example of a combinatorial optimization problem. It's similar to the ways in which you arrange airline scheduling, for example, packing of objects. Another complex system, which some people are here more familiar with than they probably would want to, are the complexities of university budgeting. Issues that we'll talk about, very technical issues, something called frustration, for example, is something that happens a lot in university budgeting. Biological and social evolution models, even things like dynamics of proteins and folding of proteins. Ideas from spin glasses have been used, are beginning to be used. So to explain a little bit about what spin glasses are and what the basic mathematical and theoretical physics ideas that are relevant there are, we begin with simpler systems. Spin glasses are disordered. I'll try to explain what that means. But non-disordered or homogeneous systems are very important and are kind of classical solid-state physics is about things like crystals, crystalline structures, ordinary magnets, superconductors, liquid crystals like in watch displays, etc. Those possess certain kinds of regularities and symmetries which help enormously in understanding them and in analyzing them. Glasses, ordinary structural glasses like window glass, those are not homogeneous systems. I'll show a diagram soon to try to give you an idea of that. Spin glasses are kind of magnetic analogs of structural glasses. Those are all examples of disordered systems in which the normal kinds of symmetries and related phenomena such as breaking of normal symmetries are absent, making them more difficult to analyze. On the other hand, and there are much more recently efforts to try to analyze them than the methods that were developed over in the 19th and 20th century for analyzing homogeneous systems. And it's still in relatively early stages, so these not all these ideas have been completely accepted, but they're working their way there. So I mentioned disordered systems. What does that mean? Let's talk about very low energy configurations of systems. So let's consider, for example, on the upper left, the crystalline structure. The atoms or molecules in a crystal are arranged in a very regular array. It's not always a square or cubic array like that. Some other structures come up, but that's an example of one. On the other hand, the molecules of a glass, like in a crystal, they're not moving around if you're at low temperature, but they are disordered. They come in kind of random-looking locations, but they're kind of stuck there for stoichiometric reasons. They just can't move around each other. That makes it much more difficult to analyze. Spin glasses are very difficult. It seems like structural glasses may be even more difficult to understand. That's something that people are working on. Magnets, including spin glasses, magnetic materials, are magnetic analogs of crystalline and glass structures. So in a homogeneous magnet, there are sort of microscopic magnetic moments associated with the individual atoms or molecules. They're like tiny microscopic bar magnets, which can point in a specific direction. And at low temperature, they're very ordered. That is to say, they're all not quite all pointing in the same direction, but mostly pointing in the same direction. If you really were at the limit of 0 temperature absolute or Celsius, they would all be pointing in exactly the same direction. And so that's what those arrows pointing there mean. A spin glass is the magnetic analog of a structural glass. That is, like a structural glass, it's the way the individual microscopic magnets point is not changing, but they seem to be completely randomly placed, like the location of the molecules in a glass. And somehow their properties have to be understood by working with that kind of disordered system. And that's what makes things both interesting and difficult to work with. So, so it's important to realize that the kind of disorder we're talking about here is not thermal disorder. If when you raise the temperature even a little bit in materials, then they start jiggling around. Either the locations in a crystal move around a little bit, or certainly the molecules in a gas move around all over the place. And similarly, the directions of the arrows of the microscopic magnets will then be fluctuating because of thermal energy. That's thermal disorder. That's not what we're talking about here. We're talking about even at very low temperature, the limit of even 0 temperature where you get ground states, you have disorder which is quenched. That is to say, it's kind of stuck there, like the locations of the molecules in a glass. Okay, so why should we be interested in such a thing? Well, if you're a condensed matter a physicist or a material scientist, spin glasses, the real laboratory spin glasses, which are magnetic alloys, which we'll talk about a little bit, represent a gap in our understanding because most of the methods that were developed in condensed matter physics were developed for these homogeneous, non-disordered systems. And a question that came up mostly in the 19th, we'll actually go back to the 18th century in a moment, that is understood quite well, but only really understood from the last century, but from condensed matter physics, is why are solids actually rigid? Because if they're made up of all these molecules and things, how come they move like one object? So there's a famous debate between two famous people from the 18th century, Bishop George Berkeley and Dr. Samuel Johnson, and it was a philosophical debate about idealism versus realism. Berkeley believed that material world didn't really exist. It was something that was created out of our sense of it. So things were all based on our observations of it, and also the observations of God. He was the bishop of the Anglican Church. So there was a famous story about this debate involving Berkeley and Johnson. And one of the advantages of giving a talk like this is that I spent some of yesterday reading up a little bit on this debate, and so I actually have a little quotation. This is from the famous book by James Boswell, The Life of Johnson. It says, "After we came out of the church, we stood talking for some time together of Bishop Berkeley's ingenious sophistry to prove the non-existence of matter and that everything in the universe is merely ideal. I observed that though we are satisfied his doctrine is not true, it is impossible to refute it. I never shall forget the alacrity with which Johnson answered, striking his foot with mighty force against a large stone till he rebounded from it. I refute it thus." So another thing that I learned yesterday is that Berkeley, which is apparently the right Anglo-Irish pronunciation of his name, is the person who the city of Berkeley was named after, but the pronunciation became Americanized, and therefore indirectly what UC Berkeley was named after, and therefore one of the streets in Irvine, Berkeley, was named after this Berkeley. We'll have two other pictures of people whose streets are named after in Irvine in a moment. So, now we're going to just go through a little bit of history of personalities involved in the thermodynamics and statistical mechanics that's important for general condensed matter physics and spin glasses, and also the use of symmetries in physics. So Boltzmann and Gibbs were 19th century physicists. Gibbs was probably the most distinguished American scientist of the 19th century. So there is a street, Gibbs Street, in University Heights, which is just a block from where I'm living at the moment. Boltzmann is very interesting. His gravestone has the formula for entropy engraved on it. He did not have a very happy life. He was actually bipolar and committed suicide, but that's another story. Actually, partly because he was afraid that his ideas were not being accepted, the atomistic theory of matter, basically, and actually it became much more accepted a few years after he killed himself. So that means you should wait a bit. Early 20th century, a very important mathematician and theoretical physicist who did work related to theoretical physics and algebra and mathematics is Emmy Noether. She studied the importance of symmetry and how its relation to conservation laws in continuum models of physics. So going into the 20th century, all of these people are very important for the relevance of symmetry and broken symmetry in various areas of physics, both particle physics, high energy physics, and statistical physics. So two of them are Nobel Prize winners, I think, Nambu and Anderson. Jeffrey Goldstone. So there is a Goldstone Street in Irvine, which I am guessing is named after him, although I didn't have time to check. The name Higgs you may have heard in the last year because the Higgs boson was experimentally observed during the last 12 months at CERN, making international headlines. The relevance for symmetry is that the Higgs boson, that when you have symmetry and broken symmetry, that is related to things like rigidity, related indirectly to why you can kick a stone and it moves, and even more esoteric is why particles have mass. Before symmetry inherent in condensed matter particle physics models is broken, then you would think that the particles would have zero mass, but then somehow the mass develops that's related to this Higgs boson. So the use of symmetry and broken symmetry and its relation to things like rigidity of stones and generalized rigidity, which is related to some of these phenomena that are mentioned there, why particles have mass, but other less esoteric things like why magnets on your refrigerator stick, why liquid crystals work, why supercurrents flow. That's the kinds of things that were done by these people. Anderson, all of these people, I believe, are still alive in their 80s and 90s. Anderson is the three, except for Anderson, were particle physicists. Anderson is a condensed matter theorist, but he developed many of the ideas which then a bit later were kind of taken into particle physics and used in other sorts of applications. So all that work had to do with homogeneous systems, not the disordered systems that I mentioned before. So what does one do for disordered systems? Well, we'll try to talk a little bit about that if I don't run out of time. Okay, let's hope this doesn't happen again. So the story that I'm trying to present is that spin glasses display features which are widespread in various kinds of complex systems, such as adaptivity, pattern formation, scale-free networks, scale-free properties, hierarchical structures, and systems that generate or incorporate large amounts of information. They seem to operate somewhere in the borderline between the border region between complete order and complete chaos. And they have those things in common with many real-world messy type problems. So that's why some of the ideas that originated with spin glasses are being used in other places. So let me briefly say something about the original spin glasses. Those were metallic alloys such as gold with a small amount of iron. The gold is inert magnetically, the iron is active. When you have a few percent iron, then you get peculiar magnetic properties. So for example, if you look at the magnetic susceptibility, those are the curves there which have a pretty sharp peak at some place. The location of the peak depends upon the percentage of the iron impurity. That seems to indicate a phase transition. Phase transitions are things like water changing into ice, or vapor and liquids transitions. A kind of a sharp transition. On the other hand, when you look at specific heat, that normally would have some kind of singular behavior at the same location. But in these materials, it doesn't do anything interesting. It has a very mild peak somewhere, but that peak is not at the same place where the susceptibility peak is. That kind of feature and other ones make the possible phase transition in these magnetic alloys very peculiar, and is what led physicists to begin trying to study them, and people like Anderson to create mathematical models of them, try to understand those, and those models led to various ideas which, as I said, have begun to be used in various completely different areas. So here's the model, the mathematical model for metallic spin glass, metallic alloy spin glass. It's extremely simple. It's a formula for the energy. The variables, the sigma x and y variables, take two values representing arrows pointing up or pointing down, plus or minus 1 values. And those coefficients, which say how the energy is, are randomly generated. That represents the quenched disorder of the system. Some of them are positive, some of them are negative. Positive ones means that the neighboring, you sum over nearest neighbors in a regular structure, locations. When that coefficient is positive, means those arrows want to be pointing in the same direction when you have very low energy, and when the negative means they want to be pointing in opposite directions. So what happens if you try to look at, understand a very low energy configuration? And suppose there are 4 neighboring locations where 3 of the values of these coefficients are positive and 1 is negative. Well, the first spin, say at the upper left corner, can point either direction. Let's say it's pointing upwards. Then the next one, if you want to lower the energy, it should, because the constant, the coupling constant between them is positive, it wants to point the same way as the first one, pointing upwards. Well, then the one down in the lower right corner, because again you have a positive constant, that one wants to point the same way as the one in the upper right corner. And so far, those 3 are kind of happy because they're obeying, so to speak, what the coupling constants are suggesting. But now you're sort of in a quandary with the next one. The next one, if it looks at its right neighbor, that's a positive coefficient, it wants to point the same way. But if it looks at its neighbor on the top, that's a negative coefficient, so it wants to point in the other way. So that has a technical term actually used in physics and other places called frustration, as you can't satisfy all the constraints. That's actually a common issue in all kinds of things, like university budgeting. And it's actually, frustration and disorder are things which are really quite common, and it's the combination of them which makes life complicated and messy and interesting, and why spin glass ideas seem to be useful in other places. So the combination of those things leads to energy landscapes or free energy landscapes which are very rugged with many peaks and valleys. Typically system is trying to find its way to as low as possible energy configuration. In biological things, you might be looking at fitness landscapes and evolution. So the dynamics gets rather complicated as the system tries to find its way towards low-lying valleys, which is low energy or high fitness in the biological context. So what are the features of spin glass that are relevant for complexity? Well, we already mentioned the two main ones, quench disorder and frustration. Another feature is very high number of possible configurations or states or outcomes, and the approximately near optimal configurations or states are very different from each other, that making it very hard to find these lowest energy configurations. There's also dynamical phenomena like slow equilibration, memory and aging, which we won't get into in this talk. All right, so here's an example of a type of problem. It says real world. The traveling salesman's version is not so real world these days, but it gives the idea of this phenomenon of many different possible solutions, which makes these problems very hard. So imagine that those points there are cities, and a traveling salesman or maybe somebody on a book tour wants to visit each one once. And let's say there are direct routes between any pair of them, and the question is, how do you arrange a route or a tour which visits all of them in a way to give the least total mileage? Well, if you have not too many cities, you can simply consider all possible tours. Here's an example of one. And calculate the mileage for that tour, and then just pick the one with the smallest mileage. That solves the problem. However, the complexity of finding that solution increases tremendously with the number of cities. There's a simple mathematical formula. If there are n cities, the number of possible tours is subtract 1 from the number of cities. The factorial means take that number multiplied by the one below it, the one 2 below it, times the one 3 below it, till you get to 1. Then divide the whole thing by 2. The factor of 2 is because we're not distinguishing between going clockwise or counterclockwise around the particular tour. If there are 5 cities, there are only 12 possibilities. You can just calculate for each of the 12 what the mileage is and pick the one with the lowest. That solves the problem. But if you're up to 10 tours, 10 cities, there are already 181,000 possible tours that you could still do with a computer. But if you have 50 cities, 49 factorial divided by 2 is really, really big. It's so big that even with the best supercomputers, it would take longer than the age of the universe to check all of them. So that's out of the question. So you need to understand some methods to get approximately close to optimal solutions and properties of them. And this is an example of combinatorial optimization problems. There are many others. And ideas that originated in spin glasses have been used in that kind of context. So things like airline scheduling, etc. Okay, so here are the points that I tried to make. So the more classical statistical physics and condensed matter physics involved homogeneous systems, but disordered systems which have quenched randomness, like in the traveling sales problem, that would be the corresponding to the locations of the cities. Those are fixed, and then you try to work with whatever you get. In the structural glass, it's the locations of the molecules, etc. And in a metallic alloy, it's where the iron atoms are located within the matrix of gold atoms. They lead to new complexities and new phenomena. There are potential applications to real-world problems. I have somewhere an example of some people who have been using spin glass ideas and trying to design, trying to understand the design of analyze the HIV virus and how you could potentially develop a vaccine by applying spin glass ideas to the sort of weak points in the protein chains that come out of HIV viruses. there are new kinds of thermodynamic behaviors which were not observed before in homogeneous systems, non-disordered systems, new types of symmetry breaking, different than the kinds that led to things like the Gibbs boson that have come out of spin glass ideas. There's various kinds of chaotic behaviors that seem to happen in spin glass-like systems. Chaotic behavior as you vary temperature, chaotic behavior as you vary the size of a system, chaotic behavior as the realization of the disorder changes. That relates these kinds of problems to things like dynamical systems in mathematics, which also have chaotic behaviors of a different kind, related to the chaotic dynamical behaviors that seem to occur in spin glasses. There are questions that arise about the way that the phenomena depend upon the spatial dimension. You can study spin glass models. Real spin glasses are three-dimensional objects, but you can study the spin glass models that energy function that was developed by Edwards and Anderson in various dimensions, 2 dimensions, 3 dimensions, 4 dimensions, etc. And it's a very interesting subject about the dimensional dependence of statistical physics and physical chemistry phenomena like critical exponents. And they seem to be quite different in spin glass and other disordered systems than they are in the classical context. So these are some of the potential uses of spin glass ideas, and it's something which is actually pretty much in its infancy, I would say, and I think things will be very interesting to see how things develop. So of course there is this book with the less than optimal cover. It's like the less than optimal traveling salesman tour, but it's the best we could do at the time. You can get a copy of that for yourself. And then, so I'd like to thank you. And these pictures don't have very much to do with spin glasses. The one on the right is from a trip to New Zealand that I took about a year or so ago. That's those of you who know that's Golem from the famous films. So that's a not real, but the one to the right of me in the other picture actually is real. That was a picture taken by my daughter in Borneo a year and a half or so ago. I suppose that fellow there was a proboscis monkey, is a complex system all of its own, or at least the harem that he runs. He's an alpha male. That's certainly a complex system. So thank you very much.
So do we have any questions for Professor Newman?
I just was wondering, I noticed a lot lately that the word microscopic is used a lot. Shouldn't it be Planck or nanoscopic? Because microscopic implies optics and...
Yeah, so I guess when I use it, you're right, but when I use it, I refer to anything much smaller than macroscopic, which are things you can touch with your hands and stuff. It depends on the context, how small you want to get. I mean, the big long-term issue in physics and chemistry in general is, how you get from a microscopic, very small-scale structural understanding of things to the large-scale behaviors, and that's something which is what Boltzmann was working on from going from molecules to gases and liquids, and what he was unhappy about. But these days, in fact, for many phenomena you want to study, start with a much smaller thing. So, at least when I use it, I'm not using it in the precise sense that you were saying, but just something much smaller than and the scale in which you eventually want to get the phenomena.
Did you define spin glasses so I missed?
Yeah, well, so so the I guess I kind of avoided trying to do that. So the original spin glasses were these laboratory metallic alloys, like an alloy which is mostly gold with a small amount of iron in it. There are other ones with a small amount of manganese and copper, which had these strange magnetic properties. But now the term has kind of expanded to be all the mathematical models which were originated beginning to try to understand those, but have taken on a life of their own, and most people study them because of the applications of those ideas into these other things like traveling salesman problems, etc.
Question? Is the stoichiometry unchanged under quenching?
Yeah, so in structural glasses, for example, if you're at sufficiently low temperature, basically the locations of the molecules are kind of frozen, so to speak, in their location, and they don't change on the time scales that you're doing experiments like measuring specific heat and things of that sort. In fact, there's a famous kind of urban legend that, so everybody agrees that things change on only on a very long time scale. There's an urban legend that if you look at the window glass in medieval cathedrals, that they're thicker towards the bottom than at the top, because things do flow on a slow scale, but it takes 1,000 years. But apparently that's not true. It actually flows on a much, much slower time scale, so that it would take the age of the universe before it thickened on the bottom. So apparently it's not true. So the answer to the question is yes, things don't change on time scales that you're interested in.
Chuck, I'd like you to maybe explain a little bit more of what spin glass ideas has helped solve or reduce the complexity of the traveling salesman problem. Because there are a lot of these non-convex optimization problems in the world, and there are the algorithms, for example, simulated annealing or genetic algorithms. So could you?
Yeah. Well. So.
Is yours?
Yes. So you mentioned the one that I would have pointed out. So there is an algorithmic computational procedure called simulated annealing, which has been used for many of these traveling salesman type problems, which actually did originate in the spin glass context. So they were trying to find the low energy configurations of spin glasses, and if you remember that rugged landscape, the problem with usual kinds of optimization algorithms is that simplest ones, basically you start somewhere and then you look at nearby configurations, and if one lowers your energy, you go down it. You're looking for a deep valley. But if you start in one of those valleys, which isn't the deepest one, you'll just go down to the bottom of that valley and you won't find the much deeper valleys. Simulated annealing is a procedure which was first done in the spin glass context. It's a procedure to model what's done in actual metallurgical situations where you try to get a metal in a low energy stable configuration by very slowly cooling it. So when it's at high temperature, it's kind of wandering around somewhere above the valleys, and you slowly lower the temperature. It goes into some valley, but since the temperature is not too low, it has a chance of getting out and finding a better valley. And so simulated annealing, so that you do physically in metallurgy to lower the temperature slowly. In this computational algorithm, you do it virtually, and that gives a chance of the system, or your calculations of the system, to find lower valleys, and there's a particular scheduling of how much you lower the simulated temperature so as to find the lowest possible valley. So I think that's one of the best examples of a technique that originated in spin glasses and then was used in other places.
So back to sort of definitional things with spin glasses. It wasn't clear to me from your diagram if the position of the spin glass, the positions are regular. it's just the spin.
Yeah, that's correct.
And
Yes.
do you get that sort of behavior from irregular, from quasi-crystalline, or anything like that, or is that?
No, no. So what you said is right. It's in fact it's not it's not the location of the spin so much that's the disorder. It's those JXYs in the energy. So which means that the interactions between different sites, sometimes positive, sometimes negative. So the way that actually arises in these real alloys is that you have, say, 2% iron atoms in this gold matrix. The locations of those are random. It's how the system was physically created that determines where they are. You don't know actually where they are. And the nature of the so-called exchange interaction between those different microscopic magnets is such that depending on the distance apart they are, sometimes it's positive and sometimes it's negative, and it's because the locations are random that leads to the couplings being random.
But it's the locations within, it's whether that site has a gold or an iron,
Yes,
not the location of the site.
Yes, exactly.
Okay.
Okay, thank you again, Professor Newman.